All right, welcome everyone. My name is Dan Zevin. I am the COFFIES undergrad engagement lead, and we've just launched something called HelioHub for all of the drive centers, really. But the focus here is on students interested in heliophysics at any level and want to start learning about what kind of careers and research you can do in heliophysics. We've got a great program for you, and we're going to kick this off soon. But right now, I want to turn it over to the other members of the HelioHub team, and I see her now. So I'll put her first. Komal, do you want to introduce yourself?
Hi everyone, I'm Komal. I'm an undergrad at Berkeley and I'm studying astrophysics and computer science. I've been working with the Coffees Drive Center for about a year now, and this summer I'll be working on the HelioHub Discord and leading the Python boot camps. So looking forward to meeting you all.
Excellent, excellent. Thank you, Komal. Let's go with Claudia next.
Hi everyone, my name's Claudia. I'm also an undergrad at UC Berkeley. I'm studying applied math and astrophysics. I've been working on the Escapade mission at SSL for a bit now, and then I just joined the Helio Hub, and I'll be working on the Discord this summer.
Fantastic, thank you. And last but not least, Phoebe.
Hi, I'm Phoebe. I just graduated from UT Austin with a double major in physics and astronomy. And last summer, I was funded by Coffees at the Boulder Solar Alliance REU. So that's how I got my feet in heliophysics, and I joined Coffees through that. And then this summer, I'm helping to plan this summer program as well.
Right, right. So Phoebe was kind of in your positions last year where we were doing this for a much smaller group of students, and this year we decided we had so much fun with that we decided this to open this up to just about everyone who wants to join. So thank you so much. Glad you're here with us, Phoebe. Does everybody see our schedule? Okay, all right. So Helio Hub. We're going to be running what we're calling the solar circuit every Tuesday for the summer, where we're going to have a number of exciting guests and topics here in the world of heliophysics. And we want this to help you consider heliophysics as a possible career and also maybe help you get your questions answered and find opportunities in heliophysics. So yeah, we hope you can join us this time every week. But we're going to start today with what's funding HelioHub, which is the Drive Centers, NASA's big investment in heliophysics, the Drive Science Centers. What are the Drive Science Centers? Well, the way NASA put it here, moving forward on the most compelling science questions in heliophysics. And you can see here, DRIVE obviously is an acronym. So is DISC, DSC for Drive Science Centers. But what does DRIVE stand for? Well, we have diversify, realize, integrate, venture, and educate. All good things to pursue. But what, how, why, what does this have to do with heliophysics? Well, the way that NASA put it was, and this is a lot, so bear with me, each Drive Science Center looks to diversify the use of observing platforms by creating new physics-based computational models that scientists can use to observe and predict space weather patterns, realize the scientific potential of existing assets, integrate those current observing platforms into programs and investigations, venture forward with new technologies by pursuing important science problems, and educate the future heliophysics workforce by mentoring early career scientists and students. That is quite a mouthful, I'm sure. And it's a lot to take in. It all does make sense when you think about it and dive into it, but it's hard to remember this. It's hard to wrap your head around this. So I've tried to, I'm going to show you here my sort of summary of what I think all this means and what it has meant to me from the very beginning of the Drive Centers. I think what really NASA is telling heliophysicists or those who want to become heliophysicists to do is to one, and you're going to learn about this as we start to dive into the different Drive Centers. One, get out of your silos. Two, be bold. Three, make breakthroughs. And 4, leave a lasting legacy. All right, I hope that summary kind of starts to fit with you and is something you could remember a little bit better as we start to explore the Drive Science Centers here. So what are the Drive Science Centers? Well, here we have a wonderful graphic that shows there are 3 of them. And of course, what you're going to see here is more acronyms. But we have 3 Drive Science Centers: COFFIES, CGS, and SHIELD. Now, this graphic is just wonderful because it kind of places them where they do their research. So you have COFFIES here at the sun, and then you have CGS as we go out into our solar system, and then we have SHIELD sort of at the edge of the solar system. And all of that will make sense very soon as we hear from our presenters. And representing COFFIES, we have Dr. Shea Hess Webber from COFFIES. From CGS, we have Tristen. Is it it's Wanner? Wanner? I forgot to ask.
It's Wanner.
Wanner. Okay, good. I'm glad you told me that. And then from SHIELD, we have Erick Powell. We are so happy to have them here, representing each of their various centers. And you're going to learn quite a bit about these centers as we go forward. And to begin, we're going to go in that order. And who do we have introducing Dr. Hess Webber?
Okay, that's me. So Dr. Shea Hess Webber is a heliophysicist at Stanford working on time-distance helioseismology for, as you know, the COFFIES Drive Center. Her research interests focus on bridging the physics gap between subsurface acoustic perturbations with observable surface features, with particular interest in coronal holes. Currently, she's working on the development for NRT acoustically derived far-side magnetic flux maps for use in flux transport, coronal, and solar wind models. She also works on outreach and advocacy as part of the COFFIES effectiveness team and also helps to run the center as a whole.
Me?
Yeah.
Okay. Just making sure. Wow, I apparently I do a lot. I didn't realize it. Okay, let me get started on COFFIES. Thank you, Dan, for the overview, and Komal for the introduction. I am indeed Shea. You can call me Shea. You don't have to call me Dr. Hess Webber. COFFIES, we love our acronym for many reasons. The main reason of which is because the actual name of the Science Center is too long to say regularly. It stands for Consequences of Fields and Flows in the Interior and Exterior of the Sun. I'm probably one of maybe 3 people that can rattle that off without having to look it up. So don't worry about remembering it. COFFIES will do just fine. And as Dan pointed out, we are focused on the sun itself and trying to come up with data-driven models of being able to predict solar activity, both on sort of smaller scales and on the length of the solar cycle. So because I'm not sure everyone's background, if this is your first solar or helio introduction, I wanted to make sure that we're all starting on the same page. So first things first, let's kind of talk about the sun. Maybe some of you have taken stellar astrophysics, maybe some of you have taken specifically things on the sun, but I didn't want to assume anything. So we're just going to kind of go out through the various layers. Starting with the core, this is where nuclear fusion happens, and it produces all of the energy and all of the light that the sun produces. That gets pushed out into the radiative zone, where essentially it acts like a solid body. And all of that energy and all of the photons get absorbed and re-emitted and absorbed and re-emitted radiatively out through about 2/3 of the sun. Where they hit a shear layer that we call the tachocline, where essentially you're going from this solid body behavior of the plasma into fluid behavior. And so that creates kind of like if you think about the surface of water and wind blowing over it, there's 2 different media. So they're rubbing against each other, different velocities, different rotation speeds. so that creates a shear layer. And then that leads into the convection zone, which is essentially from about a third of the way in through the surface, a giant, essentially point or a pot of boiling plasma, not water. But so that's where convection is happening. So that's you get these big bubbles that we maybe we'll see a picture of as I go forward. And then again, as we get close to the surface, because the nature of the plasma is changing from more of this liquid fluid state into more of a gaseous state, there's going to be another shear layer there. And we creatively call that the near surface shear layer. So that's inside the sun. As we get to the surface and outside, for some reason, which I don't agree with, the surface of the sun is considered part of the atmosphere. COFFIES obviously takes a lot of pictures, or well, as solar physicists, we take a lot of the pictures of the surface, and COFFIES studying the inside of the sun. That's really where we start, is at the surface. So if you were to look at the sun, please don't. The photosphere is what you would see. That's the official name, the scientific name for the surface. As you keep going up, you get into the low atmosphere, which we call the chromosphere. There's another transition layer where the temperature drastically spikes. If you've heard of the coronal heating problem, the corona, the outer atmosphere is very, very hot, and the transition region is where that temperature spike happens. And then outside of the corona, we're in the heliosphere. So the heliosphere goes all the way out to, it is defined as out to the edge of the solar system. So Earth is sitting inside of Sun's very outermost atmosphere. And I am assuming that you're going to hear more about that from Shield. So really what COFFIES focuses on, again, is photosphere and below down to the radiative zone. So the tachocline, that initial shear layer at the base of the convection zone itself, the near surface shear layer, and the photosphere is really where we put our science focus. And we have 4 defining science questions that we are trying to tackle within our science center. So one is thinking about large scale flows and motions inside the sun. So just like if you've studied anything about Earth's atmosphere, there's flows, we have winds, we have circulation cells. The sun has the same thing within its convection zone. So we have flows that go from the equator up to the poles and back again. We call that meridional circulation. Hopefully y'all can see my mouse. But so we have circulation cells going equator to pole and back again. We have flows that are going around the sun, like around the equator. So it actually rotates differentially in the convection zone. So the equator rotates faster than the poles. It's about 25 days at the equator, close to like 33 days at the poles. So we're trying to understand that variation. And then there's convective flows also. So again, I likened it to a pot of boiling water, trying to understand sort of how those motions interplay with the magnetic field. So trying to really understand those motions. Again, how those flows interact with the magnetic field to then create solar activity and the solar cycle. I'm not going to get into the science of this, but if people have questions, I'm happy to answer those questions. My very, very simple explanation is kind of if you think about a string and you twist the string in opposite directions at either end and it creates a kink, that's kind of what the sun is doing with its magnetic field because of all of these flows. We are trying to look into active regions, why they emerge where they do, what's causing them to emerge, where that magnetic field that's coming out through the surface of the sun is coming from, whether it's the near surface shear layer, deep in the convection zone at the tachocline, or somewhere in between. We don't really have an answer to that, so we're trying to kind of pin that down. And then also understanding how the sun relates to other stars. So there's a lot of other solar-like stars. The sun is pretty average compared to other stars in the universe. So all of those other average stars that have convection zones near the surface of the star and have rotation rates that are similar to the sun, how is what we study about the sun relevant to those stars, and what can we learn from other stars to apply to the sun? So those are sort of our 4 big science questions that we're driving into. A little bit about how the center is structured. So Dan mentioned silos, get out of your silos. Our silos are our science teams. So everybody sort of has their traditional science that they've been working in and they're experts in, and they've been approaching the sun from that standpoint, from these traditional silos. For me, helioseismology, I use waves on the surface to understand the magnetic field at the surface and inside the sun, all the way through to the other side of the sun. But I don't have a whole lot of experience doing dynamo modeling or convective modeling or tracking surface features and that sort of thing. So without that expertise, there's only so far that I can take my helioseismology without connecting it to those other things in order to make big breakthrough science. So people join COFFIES usually within a specific science team or maybe two. And then from there, we have what we call themes, so teams and the themes are more cross-cutting. So from within your science silo, we ask you or the scientists, you if you so choose, to join one of these themes where we bring people from all of the different silos together to work on particular problems. So the tachocline is one area that we don't have a firm understanding of. It was only very recently from a COFFIES early career scientists that we even had models where the tachocline was created self-consistently within the simulation. So trying to get a more physical representation of the tachocline and its role within the sun and the solar cycle is very important. Flux transport and emergence, again, talking about these active regions, where they appear, why they appear there, how they structure the solar activity and the solar cycle. And then the near surface shear layer, again, the shear layer that is there, but there are some properties that we don't really understand why those properties exist. It's too thick for one thing. So people digging in and trying to understand why, even though the shear layer that we expect to be there is there, why it's different than we expect it to be. And we developed these themes through actually a word cloud activity. One of our very first meetings that we had as a science center, we had everybody put in what they thought were the most interesting, most challenging things about the sun, about the solar cycle, about solar physics. And we basically use this to choose what our three main interdisciplinary things would be. So you see here tachoclines, quite large, flux emergence, quite large, multiple spellings of near surface shear layer. So we used a collaboration communication technique to really come together and decide together which of these challenging topics that we wanted to cover. And we also, in our leadership structure, we try to have that interlaced aspect throughout as well. So you'll see here, we kind of color code all of our different science teams. Each science team has at least two different, we call them baristas because we love our acronym, COFFIES baristas. But then at least one of those baristas helps in one of these theme directives. So there's a lot of overlap. There's a lot of pushing people to collaborate across those silo lines. We also have a lot of broadening impacts. Y'all are here because of our STEM education efforts that Dan is leading with the help of our excellent team this year. So thank you for being here, and thank you, Dan, and everyone for getting this started, kicking this off the ground. Again, this is part of RU programs that we've been leveraging, or broader efforts in terms of undergrad presence at conferences, doing mentorship across like the undergrads, grads, postdoc sort of span of early career folks. That sort of thing is all kind of funnels into STEM education. We also have a specific early career program that we call Beans, COFFIES Beans. Beans, I see the chat thing. Beans, we've named it Beans because beans really make the coffees, right? We can't do this without early career researchers. They're the ones who really do the science. And so we want to have specific programming to get them networked, to get them communicating, to get them building a cohort of their own. We also have our public outreach efforts that Brian Mendez leads. We do a lot of things. We did solar eclipse efforts and activities and events. We do what we call sidewalk outreach, where we just go out and like show people the sun. We do lots of different kinds of events. And we also have people with a lot of experience doing science on a sphere. If you've been to a museum with science on a sphere, it's pretty awesome. I highly recommend it. Lawrence Hall of Science, I believe, has one. So if you haven't seen one and you're local to the Bay Area, go check it out. And then there's the CET, which is where I come in. CET stands for Center Effectiveness Team. We are the group of people within COFFIES who are really pushing people to break out of their silos, break out of their barriers, tackle things that are risky and exciting, and work with people that they haven't worked with before, trying to make sure people are communicating effectively. All of that happens because there's a push from within the center to get people to do those things. Otherwise, we all just fall back into our silos. So that's sort of where I come into play, at least outside of the science aspect of things. And I'm happy to answer questions, talk a little bit more about the science. Happy to wait until the end for that too. Yep.
Yeah, I think we'll wait till the end just to make sure we have enough time for everybody to, but excellent graphic. Thank you so much, Shay.
That's the internet, I did not make that.
Yeah. But if you have questions for Shay, please use that Q&A function in Zoom, and then our students will keep track of the questions that are coming up.
Yeah.
All right.
I also am on Discord, so feel free to keep reaching out to me.
That's right. If you haven't joined our Discord channel, we'll mention that at the end. All right, then Claudia, I think you're going to introduce our next speaker. Yes.
Yes, please join me in welcoming Tristen Wanner, a dedicated researcher and aspiring physicist currently pursuing a direct PhD in electrical engineering at Virginia Tech with a focus in electromagnetics. Tristen is a graduate research assistant with Super Darn, collaborates with NASA Goddard's Heliophysics Department, and is part of the Center for Geospace Storms, or CGS, a NASA drive center. With a background in space physics and applied mathematics from Embry-Riddle, Tristen's work spans geomagnetic storms, auroral boundaries, and wave theory, and has been featured at conferences like AGU. Beyond research, Tristen brings experience in military training, tutoring, and teaching, along with unique passions from blacksmithing to game development.
Hi, thank you for that. Let's see if I can share my screen here. All right, do you see that? Everything correct?
Slowly loading. There we go. Okay.
All right, yes. Hello, everyone. My name is Tristen Wanner, and I want to talk to you about the Center for Geospace Storms, or CGS. I will note that I totally stole this presentation or parts from it from our principal investigator, so if this looks familiar at all, that's why. So when a lot of us are thinking about near-Earth space, we kind of just imagine the Earth and then space. You might be aware of the atmosphere, you might know of radiation belts and all that, but what does that actually look like? Well, as you might imagine, it's actually quite a bit complicated, and the main goal of our Drive Center is to develop a tool to help study it. So we are the Center for Geospace Storms, and I think the best way to describe what we do is just in our tagline here: transforming the understanding and predictability of space weather. And under that mission, we have 3 goals. We want to, 1, innovate community modeling capabilities by building a physics-based model for this near-Earth geospace. And we have particular interest when it comes to storm time geospace, and that just means if you have like a large coronal mass ejection hitting the Earth's magnetic field, what happens? What are the key physics going on there? And so our model, we like to call the multi-scale atmosphere geospace environment model, or MAGE, as you might find in some of the theming for our group. The 2, empower. We want to empower the scientific community via this MAGE model, and to really make our model stand out from the other great models that are out there modeling geospace, we want to incorporate a vast array of different data sets of observables. So like radar data, magnetometer data, other data sources to either actually constrain our model or validate our model against observed data sets. And three, of course, what do you want to do with a model like this? You want to do science. You want to discover. So this is kind of our tagline here. So discover, understand, and quantify all these different connections with all these different dynamics of space and time scales with all of our different regions of near Earth space. So what am I talking about when I say all these different regions of space? This image here kind of shows an example of all these different kind of domains that are going on. And you can see that it's quite complicated. And to make it even a step more complicated, all of these different regions have different kinds of plasma populations and neutral populations, and they have different kinds of charges and energies, and they all interact differently on different time scales. And so that can be alone challenging just to model from a high power computing standpoint. But then the physics isn't complete. And as you might have guessed, with being a NASA initiative, that's what we want to address. But because it isn't complete, and the fact that there's not a very complete array of data sources out there, some of our boundary conditions in our simulations might not be perfectly constrained. So for example, we might only have a satellite or two upstream to tell us when, or what are the solar wind parameters of that coronal mass ejection heading our way. So how does our model actually address this? Again, the model we're developing is MAGE, or the Multi-Scale Atmosphere Geospace Environment Model, and just the name alone kind of hints as our approach. What we want to do is we want to model everything from the outer geospace all the way down to the lower atmosphere. And as you can see from this picture, that requires modeling the magnetosphere, which is the magnetic field that's being stretched around the Earth with the interaction with the sun, all the way down to this tiny, tiny shell of the ionosphere and atmosphere there. But you can really take that, and up you see at the top right here, you can expand that and it becomes an entire simulation domain of its own. So another challenge is also describing what processes are important at these different regions of space, and we call those mesoscale processes. So they're not necessarily the smallest scale processes that are going on, but they're the intermediary scale processes that can have emergent behavior and affect the entire global system. So what am I saying exactly is that each of these different regions can have different important scales. So this would be a simulation that we've run for the magnetosphere. We found that having simulation resolution down to a couple Earth radii to hundreds of Earth radii is very important. You can see some of these vortices forming here. On the horizontal plane, you're looking at magnetic field strength, and on the colorful orange and purple vertical axis here, you're looking at plasma pressure. And then at the Earth is that gray little ball in the center, and then the blue lines are magnetic field lines. And you can see that there's all kinds of different fluid-like dynamics going on. Especially you can see these plasma injections that are coming from the tailward, and tailward just meaning the other direction from the sun, because when the sun is interacting with the Earth, it stretches our magnetic field away from it. And we need to resolve these processes because these little plasma balls here can enhance currents that are close to the Earth system, and those connect all the way down to the ionosphere. And as you might imagine, in the ionosphere, we might need to resolve even finer scales. And so what we're thinking about is maybe about 70 kilometers in scale. The graph you're seeing here is the northern hemisphere, I believe, looking at the ionosphere and the total electron content. This is a little bit of an old simulation. I think I saw some prettier simulations today at a conference I'm attending. But even below that, we also want to include the atmosphere because there's all kinds of different interactions that we both know of and we aren't really sure about the interactions of. So this would be a simulation that we're running. This would be, I believe this is a volcano that exploded at some point and it sent massive shock waves and that affected the ionosphere. So all of these different regions are coupled to each other intimately. And we really need to resolve all of these different spatial scales to make a faithful model about what's even just going on in the magnetosphere. Just like Coffees has themes, we have themes too. Our teams really identified three such themes. The first one here, we want to talk about the multi-scale plasma sheet transport, ring current buildup, and their global impacts through storm time geospace. And as you might not fully know what that is, the big questions involved are just how does plasma and electromagnetic energy transport through the different regions at different space and time scales? And then further than that, how does that interact with the ionosphere? And then we might have a question specifically regarding the ionosphere. How does high latitude energy deposition and momentum affect mass circulation in the atmosphere and the thermosphere? Of course, always interested in the different space and time scales as we're talking about. They're all open questions. And potentially what impacts of mass circulation in general, what does that have on the ionosphere? And then maybe even lower for our atmosphere folks, how does formation of those bubbles play in with our terrestrial atmosphere? Does it have any effect on weather pattern? Probably not, but it's at least an interesting question to look into. So when I'm talking about MAGE, what it really is a combination of a bunch of different models that are all feeding into each other. This is just done so that we can properly treat each of these different regions. So we have a ring current model. We have a model that does the electrodynamics in the ionosphere. We have a specific model for the lower atmosphere. We have some particle simulation stuff. We have a magnetohydrodynamics model, which I believe Shield will talk about as well for their stuff. And that's just a fluid simulation for considering electromagnetic field interactions. Currently, we only have a couple of these fully paired. Getting just these core ones here put together would constitute version 1 of our model. And we do have it in like the back rooms. We have it put together and people are doing simulation work, but we do plan on going open source with this at some point. I don't actually know when that is, but it should be soon. We're rewriting a lot of these models, like down there at the bottom left, you can see RCM, which stands for Rice Convection Model, if you've heard of it. A lot of our work is also working with these historical models to update them and bring them up to modern high computing standards. Going along with the mage, or you might have noticed Gamera is a monster. We named it Raiju, and we're renaming some of the stuff Hydra. Some of the people, especially the principal investigators on our team, are big fans of kaijus. So we get a lot of naming conventions from them. But if you wanted to go ahead right now and go to the NASA CCMC, which is the Community Coordinated Modeling Center, you can actually have access to this model. It's not a full release version. We call it 0.75, and it's just matching our MHD model, our ionospheric electrodynamics model, and a version of the upper atmosphere model. So we don't have a lower atmosphere yet, but that's in the works. That's all I really have for you guys today, but I thank you for being here. I'm open for questions. Veronica is a colleague of mine, and she's also here to answer your questions, especially since we're both somewhat newer to CGS, so I wanted to get some more experience on the team here.
All right. Thank you so much, Tristan. Yeah, I think we might have time here for 1 or 2 questions. Something I forgot to mention actually was the drive centers in general are really focused on modeling, right, throughout all 3 of the drive centers. I'm just curious. So we're not a space mission. The drive centers are not space missions. We're not relying on anything in orbit, but yet we're relying mainly on data, and those data do come from a lot of space missions. So Tristan, one of my questions for you is, of all these various missions that are either active or up and coming, are there any that stand out to you as absolutely vital?
It's a good question, especially considering possible funding problems that are going on right now. I would say there's a cool SMILE mission coming up that's going to be doing some soft X-ray stuff, which might be interesting. I know just at the conference, there's a lot of people that's always on a presentation talking about what they're going to be doing with SMILE. So I'm looking forward to that one. I've heard a couple talks about Tracer. I'm actually not super familiar with what Tracer is, but I know the radar folks are really interested in that. And being a part of Super Darn, I know about the radar folks. And we're trying to integrate some radar validation for our model. So all of these things kind of go hand in hand, right? So all of the missions kind of help CGS do their mission.
Fantastic. All right. All right. Let's see. Why don't we move on, and then we'll have a big round of Q&A at the end. Phoebe, I believe you're going to. Thank you very much, Tristan. Really appreciate that. Phoebe, you want to introduce our next speaker?
Okay, our final speaker is the representative from NASA SHIELD, Erick Powell. Erick is a graduate researcher at Boston University and is part of the Global Heliosphere Structure Thrust. He's working to validate models of the heliosphere using interactions of Lyman alpha emissions from stars with material in the outer heliosphere, which can be measured on Earth. Erick is the first end-to-end SHIELD PhD student running MHD simulations of the heliosphere and comparing them to these observations. Please welcome Erick.
Thank you. I'm going to share my screen here. Share this. All right. So it looks like y'all can see my screen, or did it go away?
It's loading slowly. There we
Okay.
go. Yep, yep. Now you need to go into presenter mode. Perfect, perfect.
Cool. All good? Wonderful. All right. Thank you all for giving me this opportunity to talk to you today. So I am joining you from SHIELD. I'm over at Boston University, and it was mentioned I am the first end-to-end grad student. So I finished my PhD here in March and have begun my postdoc work, still with SHIELD. And here at SHIELD, what we're really trying to understand is the heliosphere's place in the universe. All these other drive centers, they've talked about a lot of interactions between things, maybe, or mixing regions, maybe between the inner and outer regions of the sun, or between the solar wind and the magnetosphere. Here, we're looking at the heliosphere outward. So to start this, I want to point out that stars in our universe have bubbles around them, and they're known as astrospheres. Here are some observations of some nearby stars, and we see these bubbles kind of like cocoons around these stars. And our sun is just like these other stars. It also has a bubble. However, our heliosphere, which is the astrosphere around our sun, is the only known habitable astrosphere. Although these other stars have bubbles, we don't know if they're habitable, but we know for sure our own heliosphere around our sun is habitable, which really gives us good motivation to understand our heliosphere, to understand our place in the universe and how other astrospheres may promote life. So here I'm going to show a video about the heliosphere. So here's Earth. We're going to zoom out and see the sun and all the planets. And then what we start to see is this gigantic structure, not to scale. This is the heliosphere. This giant structure is made from the solar wind leaving from the sun, traveling outwards into interstellar space. And when the pressures equalize, it forms this bubble around the sun. And this bubble is very important for life on Earth. So here, what I'm showing are some cosmic ray measurements from Voyager 1 as Voyager 1 exited the heliosphere. And what we actually got from these observations between after about 2012 was we saw that the heliosphere shields the solar system from galactic cosmic rays. And in particular, it shields about 70% of the cosmic rays that are seen outside the heliosphere. These are cosmic rays up to 1 GeV, but this is really important because these really high energy particles are shielded from the Earth's perspective. And that's very important for life because these cosmic rays have a lot of energy, and when deposited into either the Earth or people, it can be very damaging. So, to talk about the scales about the heliosphere, how big this structure is, this is just a pretty graphic where the sun's right here at the center right here, and the overall structure of the heliosphere is about 120 AU, where the AU, if you're not familiar, is the distance between the sun and Earth. So it's a very large structure, larger than the entire solar system. And we've had a lot of missions that have been able to get out far, but not super far. So, for example, Pioneer 10 and 11, they made it tens of AU out to about 80. We've had Cassini out to about 10. IBEX was a mission at 1 AU, but allowed us to understand outside of 1 AU. And some of the most important missions for all of our work have been Voyager 1, Voyager 2, and New Horizons. These spacecraft, specifically Voyager 1 and Voyager 2, were launched in 1977, and they revealed unparalleled observations for understanding our heliosphere. They've they've encountered the largest structures in the heliosphere and have made it into interstellar space, where the sun's influence or the heliosphere is no longer the dominant structure you're feeling. And New Horizons, launched in the early 2000s, has revealed a lot of stuff that Voyager 1 and 2 were never designed to observe, and has really filled in the picture that Voyager 1 and Voyager 2 left behind. And very, very soon, we have a mission called IMAP coming out, which is going to be very useful for filling in a lot of the gaps that IBEX left, looking at some of the features of the heliosphere. And potentially, hopefully, eventually, we get an interstellar probe, a mission designed to observe the interstellar medium. This would bring so much light into our research and be so useful. So the heliosphere is not very well known, and at Shield, we are trying to answer a few questions. So, for the first question we want to understand is, what is the global structure of the heliosphere? We still, to this day, do not have a grasp on what the heliosphere looks like. One, because it's a gigantic object and it's very hard to observe. But two, because our models aren't perfect. And as everyone else talked about, these models need improvement. They need improved physics. They need improved observations and all the other things in between. There's very important concepts such as pickup ions. These are ions created from the interstellar medium, and they are very important for the structure of the heliosphere, and we still don't understand exactly where they go throughout the heliosphere, so we're trying to understand their role. We also really don't understand the interstellar medium. So the heliosphere, created from the sun, where the inner boundary is driven by the solar wind. In our models, the outer boundary is the interstellar medium. And this is the region outside of the sun's influence. And you may be interested to hear that we really don't understand it very well. We have Voyager 1 and Voyager 2 out there, but it's very hard. It's still very near the heliosphere, so it hasn't understood it. They can't see pristine interstellar medium. And all of our observations, it's very hard to observe this very tenuous plasma out there. And so the interstellar medium is 50% of this system, and we still don't understand it very well. So at Shield, we're trying to use different observables. Specifically, what I use is Lyman alpha to try to understand the local interstellar medium. And finally, we have one of our questions is about cosmic rays, because cosmic rays are very important for habitability and for the structure of the heliosphere, and they're still poorly understood. Our models are now able to look at how these cosmic rays evolve over time, but it's a very complicated system, just like all the problems that the drive centers are trying to understand. And some of the processes that we have some experts for is understanding turbulence in the heliosphere and reconnection, two very big, broad categories of plasma physics that you have to apply to the specific problem, specifically the heliosphere. It's very difficult. And here we also have some of the observations. We got Cassini observations, New Horizons, Voyager, and IBEX. All these observations are crucial for understanding our heliosphere. And so here on the left, this is highlighting the first question. What is the shape of the heliosphere? And the traditional understanding is this very long comet-like. If you see this, here's the sun, interstellar medium's right in the middle, and it flows this very long connected tail. However, some work has been done suggesting that may not be the case, and the heliosphere may have a split croissant-shaped heliosphere. And so these questions actually play it's not a superficial question. They actually play a very important role in governing how cosmic rays enter the heliosphere. So these things are what we're trying to understand. And then to talk about the interstellar medium, here in this figure, the sun's right at the center, and what this dusty material around is supposed to represent the interstellar medium. We know that the sun moves throughout time, specifically 18 parsecs per million years. And what that lets us know is the interstellar medium that the sun or the heliosphere is interacting with today is not necessarily what the interstellar medium the sun was interacting with in the past. And this is really important for understanding. If we understand our sun's time history, we may be able to apply this to astrospheres, to other stellar systems. So when we're thinking about the past history of Earth, if we look back a few million years ago, the sun was in a very different region of the interstellar medium. And what happened was the heliosphere would have collapsed because we found a very dense part of the interstellar medium we think the heliosphere went through. So here, now the scale, instead of hundreds of AU, it has collapsed down to less than 1 AU. And if you know what an AU is, you know that means that Earth potentially would be outside of the heliosphere. This is an environment that today we could never even imagine because the heliosphere engulfs the entirety of the orbit. But this has some really interesting implications for example, the climate of Earth, or just how things evolve over time on Earth. So we are also trying to look outward from heliophysics and connect to astrophysics too. And it's been really exciting to be able to talk to scientists from all over the world with all these various different expertise. And so with that, I'll leave with some contact stuff and I'll take some questions if we got time.
That was great. Thank you so much, Erick. Something I'm always forgetting, and I saw in one of your graphics there, heliopause versus heliosheath. Can you tell us the difference here?
Oh yes, sorry. I didn't lay out the standard diagram. So the helio sheath is when the supersonic solar wind, it exits the sun at supersonic speed. When it becomes subsonic, that is the helio sheath. The heliopause is the boundary between the subsonic solar wind and the interstellar medium. So the heliopause is the outer boundary where it goes from sun influence to interstellar medium connection.
Okay, great. Thank you. All right, I think we're just going to open the floor now then to anybody who has any questions, and I'm going to let the HelioHub team manage this. Claudia, are you there? Do we have any questions? Or somebody?
There was a question that was asked in Q&A, but it's already been answered.
Well, oh, Shea answered. Shea, do you want to just kind of reiterate this one for the video at least?
Yeah, sure. So, well, if Aria wants to ask the question openly, I'm happy to do that. But also,
Yeah, repeat performance. Sure, why not?
Aria, do you want to ask it?
Okay, sure. Um, Hello. Thank you again, Shay. I was wondering if your team specifically, like your team's models and data, could anticipate coronal holes or like predict the movement information of coronal holes, or if that isn't possible because that information bleeds into the solar layers beyond the core COFFIES focus of like the internal fields and flows.
Yeah, so this is actually a great question because it's kind of a point of contention in the field. They're called coronal holes because originally they were presumed to be dominated or really controlled and only exist in the atmosphere. I am strongly of the opinion that that is not true. They are at least seated in the photosphere, and for larger, more stable coronal holes, especially the polar holes at solar minimum, they should propagate deeper down, and we should see signatures of them. And they certainly have implications for the solar cycle and the solar dynamo. That being said, there isn't actually anybody in coffee specifically looking at coronal holes at the moment, especially from a modeling standpoint. We have modelers who do surface flux transport and who look at magnetism on the surface and try to track and predict how it's going to evolve. But mostly the interest there is more towards the active regions and the large scale open magnetic flux. So again, like the polar coronal holes and how, or the polar open flux and how that opens up over the course of the solar cycle. There's not actually anybody who's digging into coronal holes specifically and trying to look at how they develop from the surface or below standpoint. So something I'm definitely interested in, but and actually my PhD was on it, but not something that there's active research on at the moment.
Excellent, thank you. Aria, do you have any follow-up?
I think that was sufficient. Thank you, Shay. And if you have follow-up, I'll put them in chat.
Aria, where are you from, by the way?
I grew up in LA and Dubai, but right now I'm living in SF.
Oh, okay. So you're a UC Berkeley student?
Yes. Is that what you meant? Sorry.
Yeah,
Yes.
yeah.
I'm from
Excellent.
yes, I'm a newly UC Berkeley grad.
Fantastic. All right. Claudia, any other question?
Yeah, there's a question in the Q&A from Mariana if you want to ask, or I can read it out.
No, I can ask. I know there's many unanswered questions about the heliosphere that are aimed to be answered by future missions, but what could be one idea specifically that we could focus on since it's very wide?
So I think you had a really good point that there's a lot of questions open. One of the things that keeps me up at night is what is the magnetic field in the interstellar medium? I think magnetic fields play a really big role and are underappreciated. So I hope we can understand that going forward with Helio.
All right, yeah, that gives me an idea. Thank you.
Anybody else want to tackle that one? Other thoughts?
I have a lot of thoughts, but
Yeah, okay.
I don't have to share them all.
I see we have a new question though. Oh,
Oh,
you want to go, Shay? Go ahead.
no, go for it. I'm
Okay.
happy for more questions.
Claudia, who's the next?
Ed asked a question. Ed, if you want to ask it in person or ask on Zoom, you're more than welcome to, or I can read it out.
Sure. Hello. So I was just wondering if somebody could explain the way that the plot slopes the slope of the plot increases so dramatically on the cosmic ray measurements at Voyager 1 from about, I think it was like 2012 and a half.
Yeah, so that was the plot that I showed, right?
Yes.
So that is due to the heliosphere filtering out the cosmic rays. It's hard for the cosmic rays to enter the heliosphere, which is why it's such a sharp increase when it's going from heliosphere to the interstellar medium. The interstellar medium just has cosmic rays floating in all directions, basically.
Okay, I see. Thank you.
Ed, where are you from?
I'm from New Mexico, New Mexico State University.
Ah, fantastic. And I believe, Mariana, you are also New Mexico, yeah? If you're the Mariana I'm thinking of.
Yes, same from New Mexico State University.
Excellent, excellent. Welcome, welcome. Claudia, how's it going with the Q&A?
No new ones, Dan.
Yeah? All right. Well, I think people can raise their hands at this point, if they want. Or
Um, Actually, I do have a quick question. With the kind of global structure of the heliosphere that was shown, what is kind of the biggest cause we could say of like all the asymmetries that are in it?
So you're talking the very large scale structure, it's not symmetric, right? So the most at the base level, that's the asymmetries in the interstellar medium and the solar wind. So, for example, the interstellar medium has a magnetic field that is not perfectly flat. So that has a role in shaping the heliosphere. But also, depending on what models we run, sometimes the solar wind doesn't have like a flat condition, symmetric in all directions. The sun is not a symmetric system, so that also influences the symmetries in the heliosphere as well.
doesn't
Gotcha.
Marav call it a croissant?
Yes, she loves to talk about the croissant.
Yeah, we need CGS to have some food type acronym because then we'll have coffees, croissants, and something else.
I can start petitioning for some renames.
Thank you.
Fantastic. Sophia, you just graduated, right?
I sure did. Just graduated from the University of Michigan. And I'll be starting my space physics PhD at UT San Antonio, this fall.
Fantastic.
Thank you.
Glad you're here with us. Yes, this is wonderful. All right, Claudia, what's Q&A? Any other questions? Got any of your own? No? Okay. Well, unless there's anything else, let's give
I have a question
Oh,
for
there you go.
all the students, the participants. How many of you is this your first foray into space physics, heliophysics? Have you all experienced it before and know it and love it and came back, or this is new?
It was pretty new for me.
Awesome. Welcome.
Follow up. I've been liking it.
Also pretty new. I got to do a research project in heliophysics, but I guess this summer I'm taking it easy, but I'm also trying to like stay up to date with everything that's happening. So I kind of go in to my PhD like a little more informed.
By the way, just out of curiosity, hopefully you all know how to use the raise your hand function if you're not from UC Berkeley. Yeah, Shay, I know. Yeah, yeah. Wait a minute. So we just had a number of people from non-UC Berkeley, so they should be raising their hand. Okay, I just wanted to get kind of a 1, 2, 3, 4. Cool, cool. All right. Well, I'm glad we're getting a much broader reach than Berkeley because we started advertising here at Berkeley. Oh, wonderful. Okay, even more. Fantastic. All right. Well, let's give a big, big, warm welcome I mean, well, a big thank you to all our presenters. It was just fantastic. I think to once again, not only hear from them, but kind of get this broad view of the Drive Science Centers and get your input. It was really great. I think this is a great start. Thank you so much. Students, I hope you can join us weekly. Next week, we'll be diving into the actual methodologies that heliophysicists use to do their research. Everything from computational modeling to actually mission launch and instrument design. So that should be an exciting panel as well. And we hope you can join us. Same time, same channel here. All right. Yeah. Thank you, Ed. Really glad to have you here. Anything else? Kamal, Phoebe, Claudia, am I forgetting anything? All right. Well, we'll see you all again next week, I hope. And again, Shea, Tristen, Erick, and Veronica, thank you so much for being here with us. We really, really appreciated this. All right. See ya. See y'all.
Thanks for the invite.
Bye.
I just wanted to pipe in that if anyone wants to reach out to us at CGS and talk about near Earth geophysics, do so. You can find us on the Center for Geospace website.
Fantastic. Is there a general email or?
Mine is going to be my Virginia Tech email, so it'll be wtristan@vt.edu.
Okay. Excellent. All right. I'm going to stop the recording. Here we go.